Welcome to an hour of HealthMade Radio. HealthMade is a community for natural health seekers where we educate people about common health conditions and share extensive research on the most effective natural health treatments and promote legislation that protects our health freedoms. A core concept belief is in the innate intelligence and healing power of the body, and if properly supported spiritually, emotionally, and nutritionally, it can find its way back to health. HealthMade Radio will bring information from integrative health experts throughout the world. Health is what you make it. I'm Dr. Michael Karlfeldt, and I will be your host. Today's guest is Dr. Shohini Ghose. Dr. Shohini Ghose is a multi-award-winning quantum physicist and professor of physics and computer science at Wilfrid Laurier University. She's the president of the Canadian Association of Physicists, the co-editor-in-chief of the Canadian Journal of Physics, and the director of the Laurier Center for Women in Science. 2019, she's featured among 25 women from around the world in a UNESCO exhibit in Paris, France, as one of the most remarkable women in technology. Dr. Ghose, I'm so excited to have you on the show today, and I know we're going to be discussing something that may be a little bit challenging for people to really grasp, and that is quantum computing and how that relates to us and the impact it's going to have in our world. Thank you so much.
Thank you for inviting me, and it's a pleasure to talk to you.
So I'm curious. You are a lady. You're from India, and you went for quantum physics. So how did that all come about? I would assume that was not kind of the first thing that your parents suggested that you go for.
You mean everybody doesn't do that?
Exactly. That's like the first thing that rolls off the tongue, you know.
No, it's, of course, you're right. It is a good question. Personally, my own family was always very supportive. My parents essentially told me, look, you know, whatever you want to do is fine. They really supported us, and, you know, it was all about doing what we really felt passionate about and, you know, supporting learning and knowledge. So I feel very lucky that they were that, you know, always open to any direction I wanted to go. It's not like they had, you know, expectations about, you know, me being in a particular career or not. So that was really very freeing, and I think that certainly helped me to explore. And when I did explore, I got inspired by all kinds of, you know, wonderful, you know, role models and experiences and ideas that I heard about. For example, when I was a kid, the first Indian astronaut went to space, Rakesh Sharma. So that to me was so inspiring. And, you know, I always dreamed about exploring new worlds, and I didn't make it to space, maybe someday in the future, but I feel like I do explore new worlds by, you know, looking into the weird quantum world. So, yeah, that's my story.
And it's so that the quantum world, I mean, I'm obviously as a naturopathic doctor, I'm looking towards, you know, the health of the body and trying to understand the body. And to me, that kind of step into the quantum world and now also the quantum computing, I think that is really fascinating, and it's a kind of movement of us to be able to understand how we as human being functions, how information is relayed from cell to cell, maybe from human, and then also using technology, obviously, to even enhance that.
Yeah, so I think it's early days for quantum computing. We're sort of taking baby steps right now, so I think we're very far from understanding things like, you know, how humans, you know, human cells work at that quantum level in any complete way. But it is certainly exciting, and there's absolutely application on a computational level where better computing can help us to do better models of molecules and understand their properties, and therefore develop things like, you know, better treatments and so on.
So for listeners, what is the difference? I mean, we're used to normal computers where It's guided by, zeros and ones, and you have these little bits and transistors, and they turn on and turn off, and that gives us the information that we're wanting. How is a quantum computer different than that?
So that was a great summary of regular, what we call classical computers. In terms of bits, that is the fundamental unit of computing. And yes, amazingly, all logic can be boiled down to zeros and ones combining in different ways. And, on and off switches are essentially zeros and ones. That's why we can do computing. But turns out that's actually one particular approach to computing. And quantum is teaching us that you can have a much broader way of thinking about computing. So instead of limiting ourselves just to 0 and 1, we can actually conceive of a model of computing based on some combination of 0 and 1 where there's only a likelihood of a 0. It's not that the bit, the quantum bit, which we call a qubit, it's not that it has to be exactly a 0 or has to be exactly a 1, but it can be uncertain. And in fact, this kind of quantum uncertainty is a fundamental property of particles like electrons and protons and photons, which we can't really get around. It's there. It's just like, how gravity is there. You can't get around it. So given that it's there, it's always been kind of a weird property that we've been avoiding when we physicists try to develop technologies and computing power. But I think the transformation happened when we reframed our thinking around the 80s and realized that why ignore this? Maybe we can just develop better computing algorithms that harness this weird uncertainty. And even if the quantum bit is not exactly precisely 0 or 1, this combination actually allows for a much larger computing space and perhaps ways of parallel computing and doing things that we couldn't do before, such as hiding information in the uncertainty. All of this combined led to a revolution in thinking about computing itself, and then thinking about how to build computers that are not just limited to zeros and ones, but can harness this whole space of any possible combination of 0 and 1. It turns out that's powerful, and that is the basis of quantum computing.
So I'm curious, because you're used to then punching in a question or you're programming, and you want the very specific result at the end. I mean, how can you use something that has all that uncertainty connected to it, and how can you use that to spit out something that is certain, a certain result?
That's a really great question. So you're absolutely right. When we ask a question, usually we ask it as something specific that we want to know. So the input is not some quantum uncertain format. The input is still very much, zeros and ones in the forms that we are used to. And the output will also be a specific format and hopefully a precise answer to some computational task. But in between, what the computer itself does is it takes that input question and converts it using some kind of an algorithm or a logic system that's based on the laws of quantum physics into this more fluid information where it's a combination not just of zeros and ones, but these probability, what we call superpositions of probabilities of zeros and ones. And one way to think about it is to imagine, instead of just, specifically switches going on and off and, current flowing inside a regular computer, think of a more fluid, almost like, let's say, water flowing inside a computer where, things are not just on and off, but they can flow in such a way that the algorithm is written to make the information flow remain spread out so that you can do all kinds of parallel information. And then eventually, if you're clever enough with your algorithm, you can make the flow flow towards the right answer. And I know this sounds really weird. And of course, any analogy for quantum doesn't work because it's outside of our everyday experience. We don't live in this world of fluid identities, unfortunately, to some level. So it's hard for us to think of something that's not specifically 0 or 1. But if you can imagine this kind of more fluid information, what's happening inside the computer is some kind of a set of commands that, of course, we give the computer through programming. that manages this flowing information in such a way that the calculation flows to the right answer. And sometimes, flowing somewhere is faster than actually going there in discrete steps, which is what our regular computer does. So that's sort of the best picture I can draw, unfortunately, without getting into the specific mathematics of it.
Yeah, and I appreciate that, because then you would lose all of us. So, it almost sounds like when you're trying to explain it, it's like when a Buddhist is trying to explain nirvana, and then the best explanation is it's not this and it's not that. So meaning that you can't put a finger on it and say that this is what's taking place, or this is, it's not an exact point, so to say, but it's that kind of a fluid, and it's almost like it's driven by intention, like we have in a lot of people that believe in quantum. I interviewed Dr. Goswami, Amit Goswami, wrote all the different quantum medicine, the different quantum books, and how intention really drives the process to get to a resolution. And it's almost like the intention kind of drives the process towards the solution that you're looking for, in a way. So that's kind of the control, so to say, as you're moving through this fluidity. Am I completely off base?
So actually, I think certainly there's metaphorical connections between what some of these Eastern philosophies have been talking for a long time in terms of, how we are not necessarily separate from the world, and there's a question of what is reality itself. So there are lots of, very interesting, deep, metaphorical, philosophical questions there. On the physical level, in terms of whether intention drives something or not, there is no evidence that at the level of human behavior that we have, quantum ways of driving things. In fact, we can, very clearly show through the physical processes that at the scale that we function, there aren't any quantum level superpositions that I was describing, and there's a physical reason for that. It's a matter of how particles interact with each other. So according to the actual theory of quantum physics, at our scale, the physics, actually, the interactions will sadly remove these interesting quantum superpositions, unless you can isolate every single particle from every other particle in the universe. Then you might see quantum behavior. But other than that, we know that the mathematics and the theory tells us that how these quantum effects disappear, which is why we don't see superpositions of currents being on and off at the same time, and we don't see coins being heads and tails at the same time and things like this. We do understand that process. So yes, there's interesting ideas from different cultures around this question of what is reality, sure. But being able to observe quantum effects at the human scale is not what the theories telling us right now.
No, exactly. We're going to take a quick break. You're listening to Health Made Radio. I'm Dr. Michael Karlfeldt. I'm here with Dr. Shohini Ghose.
Now, back to Health Made Radio with your host, Dr. Michael Karlfeldt.
Welcome back to Health Made Radio. I'm Dr. Michael Karlfeldt. I'm here with quantum physicist Shohini Ghose, and we're discussing quantum computing and the different implications and implementations of that technology that's moving forward. So, and I thought that was an interesting point that you're bringing. So you can isolate these things on a much smaller scale. I mean, you got to be on the quantum scale, but then there are different rules that guides the universe. When you have bigger objects, and like you mentioned, if you have all these different atoms or molecules that are functioning together, I know there's somebody that was talking about that you create a decoherence, meaning that it's hard to have all these different atoms, being coherent together. They get all jumbled, and then it's hard to isolate them, these different behaviors on a larger scale. So that's why we have more of the kind of classical physics for larger objects.
That's right. So another way to think about it is that if you have a single electron, for example, which has all these quantum properties and you know all the information, and it's isolated somehow so that nothing can leak out from whatever containment or isolated, place or, way that you have isolated this electron, then absolutely we know that the fundamental theory of the universe is quantum theory. So it will apply to this one single isolated particle if the entire universe for this electron is just that one, there's only that one particle and nothing else. But let's say you bring another electron and introduce it into this, artificial universe, then they start interacting with each other. And then if one of the electrons happens to leave that isolated space, then it takes some of that it takes some of the information of the interaction with it when it leaves. So in the tiny universe of the individual electron, some information has leaked out. And somehow that kind of leaking of information is what we call decoherence. And it takes away the quantum properties more than the classical properties. And that's why what's left over is our classical world. And because we are made up of so many electrons and particles constantly interacting in ways where, things leave our immediate environment and we can't control it, it's like information is leaking around everywhere. So we're constantly being reduced to classical objects, although the underlying theory is always quantum theory. It's just it manifests itself in this way because of this information leaking problem, which we call decoherence.
And so, so you're talking using one of the components. You were talking about decoherence, but then there's also the component of quantum entanglement. So that is when you have two different objects or two different particles, and somehow you kind of connect them, entangle them in some fashion, and then the information between them can be passed back and forth, right?
Right. So, back in our, this artificial universe of just the two electrons, when they interact with each other, that's exactly what happens. They become entangled in such a way that they become in sync, meaning let's say that you want to create a little computer and, you want to lock them to be either 0 or 1. You can do that through entanglement, but keep in mind that there's always this quantum uncertainty. So although they are always in sync, individually they're fluid. So their fluidity is in sync, let's put it that way. And that's what we call entanglement. However, if one of the electrons leaves that universe, then it takes this information because of entanglement. It's what actually causes decoherence as well. It's taking that very interesting, synced uncertainty away with it. So if you don't lose the information, then and you preserve all of that connection in this in the case of the two particles, then that kind of a connection, entanglement, is very powerful. And that's what we try to do in a quantum computer, where we create this interaction, get these particles to become entangled, but make sure that we don't lose one of the particles or lose the information that connects the two particles. If we are able to do that and avoid decoherence, then it becomes very powerful as a resource that we then can use for doing computing. So there are two sides of the same coin. Losing entanglement is very bad. It causes decoherence and classical behavior, but maintaining it is powerful, and then we can use it as a control knob and do better computing. And
so what can a quantum computer do that a normal computer cannot do? I mean, have we reached, is there a functional quantum computer now?
Yes, so actually there are a few different prototype quantum computers, but as I was saying, this is early days. So the computers we're talking about are more like test, toy computers that have been developed and demonstrated to work, meaning you can run some toy problems on these computers, which of course we could also do on our regular computers. But just to prove that the quantum computer works, we can run a problem and see whether it gives you the right result, and also compare it to the time taken to do the same task on a classical computer. and the steps that you use on a classical computer and see whether there's a difference or not. So that level of computers do exist. For example, IBM has developed such a computer. Google has a working quantum computer. There are some newer companies such as D-Wave that is developing, well, it's a quantum processor. It's not a full-scale quantum computer, but it has certain problems that it can address in a quantum way. And there are some other such companies that have developed quantum prototype computers. None of them are powerful enough or large-scale enough to really, access a huge amount of power to really completely beat out regular computers right now. But in principle, it's a matter of engineering to be able to scale this up. It's definitely very challenging. As I said, decoherence is always lurking. So you have to constantly be careful that you don't lose information, you don't have any noise in the system. So that's a huge engineering challenge. Perhaps it's so big that we wouldn't have the resources to do it efficiently. We don't even know the answer to that. But if it's possible, and of course all these big companies are pouring resources into solving that kind of problem, if it's possible, then we are going to be able to scale up, and that's when things will start getting very interesting.
Fascinating. We're going to take a quick break. You're listening to Health Made Radio. I'm Dr. Michael Karlfeldt. I'm here with Dr. Shohini Ghose. She's a quantum physicist.
Now, back to Health Made Radio with your host, Dr. Michael Karlfeldt.
Welcome back to Health Made Radio. I'm Dr. Michael Karlfeldt. I'm here with quantum physicist Shohini Ghose. We're discussing quantum computing and the implications that it has in our world. So currently we have quantum computers. They are functioning kind of at a lower scale. You're mentioning that it's mostly the engineering issues that is limiting its ability. Is there something that a quantum computer can do now that would take a very long time for a regular computer to do?
Yes. So very recently, Google actually announced that they had performed a calculation on their quantum computer that in principle can still be done on current supercomputers, but it would take all of the best and most powerful supercomputers of the world today working, over a couple of days or something like this to be able to solve the same problem that was solved in seconds on Google's computer. So in that sense, they have been able to, essentially rig up, a fairly, complicated-looking task, which is actually very hard to explain even what the task is. It's fairly mathematical. But technically, it's a task that, the quantum computer can do more efficiently than the classical computer. It may not be necessarily immediately useful for, something like, perhaps solving transportation problems or healthcare problems in the world. But it's again it's a test case, a benchmarking kind of problem. So that has been done, but it's still, this bigger challenge of how to take a problem like that and then make a more realistic problem, such as perhaps, solving the world's transportation problems or analyzing global climate data. That scale of quantum computer we still haven't got to.
And so, and what are some of the kind of challenges you said engineering challenges. I mean, what does that involve? Are there certain type of environments or certain, how does a quantum computer differ in structure and environment that it needs to operate within than a normal computer?
Right. So I can tell you about some of the more common approaches to building a quantum computer. It doesn't mean that there's only one approach. There are many different approaches, but what's usually done, for example, what IBM is doing and what Google is doing is to build a quantum computer using something called SQUIDs, which are superconducting quantum interference devices. And remember what I said about how these quantum bits have to be really, really isolated, meaning you can't allow any information to be lost to the environment, no noise. All of that means that these devices have to be kept at very, very cold temperatures, because any heat is like a method for these quantum bits to lose their quantum information. And so any kind of heating is a problem. So overheating, I mean, we already know this is a problem with our regular computers. Occasionally they overheat. For quantum computers, overheating is a whole different level because we're talking about cooling these devices to temperatures that are colder than outer space. So, even the tiniest amount of heat is a very bad thing. So when we say engineering challenges, maybe it's a bit of an understatement. We're talking literally astronomical challenges.
Yeah, I would say that would be a challenge to keep temperature colder than outer space. And do that.
It's kind of incredible that it is even possible at all, but it is, in fact.
Yeah, that is fascinating to me. So, yeah. And you're talking about these quantum bits, and I would assume, the more quantum bits you have, the more powerful the computer is. How many quantum bits do we have now, and like the IBM computer that you were talking about?
So IBM's most basic model has only 5 quantum bits, or qubits, believe it or not. And so that's what I mean by a very small test computer. But they have another working larger scale computer around 50 qubits. So I'd say currently the computers around the world, we're talking about on the order of tens of qubits. Now, to do something really important, meaning game-changing, would require, I'd say, at least another factor of 10. So we should have hundreds of qubits. If we had hundreds of qubits, we could probably start calculating, problems such as I was saying, understanding the properties of different materials, and so build better materials design, maybe better solar cells, for example, or we could develop, think about molecules for, things like better medications and treatments, or better ways to develop chemicals that are not harmful for the environment and things like this. So those are within reach. But there's this other big application that quantum computing could be used for, which is really what got everybody excited in this field in the first place. And this is, believe it or not, just this question of factoring large numbers. So if I asked you to give me the factors of the number 21, that's pretty easy. 3 times 7 is 21. But if I asked you, what's the factors of, let's say, 169 or 3,758 or whatever, it gets harder and harder. And if you go to numbers that have about 100 or 200 digits, turns out it's a very, very difficult problem to find what are the factors of that number. And then that may seem like a kind of boring math problem, but turns out this is the math problem that is used for encryption around the world today. The idea being that your passwords somehow are built around, a secret number, meaning a very large number whose prime factors are not publicly known. So any hacker who wants to decrypt your password would need to be able to figure out how to factor this large number. And since it's a very difficult problem and supercomputers can't do it, that's what our encryption is based on. A quantum computer with, orders of several hundreds of qubits could, in principle, crack those encryption algorithms in a matter of seconds. So all of the current existing encryption would immediately be vulnerable, and of course that worries a lot of people. And that's been the driving force behind developing these larger scale quantum computers. And that would take a little bit more time because, of course, we'd have to scale up and add many more qubits. And every time you add a qubit, you have to worry about noise and heating and decoherence.
Yeah.
So that's what people are working on now.
And obviously, we have health records that we want to keep safe, 10 years from now, or financial records and security, national security records that we want to keep safe. So you have to then almost make the records safe based upon the technology that will be here 10 years from now.
That's exactly right. Absolutely. We can't afford to wait until those quantum computers exist, because it takes a lot of time to, change over the entire world's infrastructure. So, better get on it.
Yeah, exactly. And also you mentioned something like drug development. I mean, why would we need quantum computing to do good drug development? I mean, aren't we good at that already?
We are fairly good at it, but turns out that if you have let's say a molecule with, maybe 10 or 15 atoms that are connected together, keep in mind that, atoms are made up of, quantum particles like electrons and protons in the nucleus. So they all have quantum properties. And turns out that if you try to use a regular computer to calculate all of the quantum properties of a molecule with maybe, let's say, 20 atoms in it, it turns out to be computationally very, very complicated because a regular computer is not equipped to handle quantum kinds of calculations very easily because it's not the way it operates. But a quantum computer itself would function on quantum properties. So it's basically like running a native program on a quantum computer. It's what we call a quantum simulator. So it would be much more matched to the problem it's trying to solve, which is the behavior and properties of different molecules at a level where if we can understand all of the properties of how it interacts with, let's say, molecules in our body, or, with other molecules that could be other drugs, then that helps us understand things like how perhaps, for example, vaccines work and so on. So this is just about gathering better information to make more informed choices about our healthcare and what would be the best treatments to use.
So it sounds like then we need the type of computer that matches the environment that you're computing.
Exactly.
So more of the classical physics, which are bigger objects, and we can compute more with zeros and ones. It's more of that certainty principle because it is such a large scale. But then when you bring it down to the molecules, which obviously you have drugs and interactions of biological systems, we have all that uncertainty. And then it's better to have then a calculating tool that matches those principles.
That's exactly right.
Fascinating. We're going to take a quick break. You're listening to Health Made Radio. I'm Dr. Michael Karlfeldt. I'm here with Dr. Ghose. She's a quantum physicist.
Now, back to Health Made Radio with your host, Dr. Michael Karlfeldt.
Welcome back to Health Made Radio. I'm Dr. Michael Karlfeldt. I'm here with Dr. Shohini Ghose. She is a multi-award-winning quantum physicist, and we get the pleasure to talk about quantum computing, which I know is on everybody's mind. Well, it's on a lot of people's minds. So why you're talking about this factoring issue, finding the different factors for large numbers and the security, and also we talked about drug development. I know also there's a huge amount of money that's going into like artificial intelligence. I mean, are there certain areas where these two intertwine, where you can have like quantum artificial intelligence?
Yes, in fact, the area of quantum machine learning is a new and growing area. And essentially what it involves is exploring how perhaps quantum computers in the future could use machine learning techniques to, develop better algorithms that are more quantum-based. But the other way around also works, where machine learning itself could be used to improve the quantum computing itself. So it's a very new field right now. And as I said, because we don't actually have large-scale quantum computers, we can't run big data kind of analysis on a quantum computer anyway. So right now we're talking about just developing software techniques and, mathematical modeling and frameworks so that when we have larger scale quantum computers, we can use machine learning-based algorithms to sort of use the best of both worlds, if you like, and address all of our big data problems.
So with this then, I mean, where do you see, if you've had kind of binoculars and you were able to look into the future, let's say 10, 15 years from now, I mean, what would be your prediction? I mean, what would you expect when because you've been at this for quite some time, and you've been, your team has been leaders in this area. So how would you see it develop, now 10, 15 years from now?
That's actually a really good question. And, I always am, cautious about answering these kinds of questions because every time. Yes, exactly. So every time we think we can predict technology, we fail miserably. And that's both good and bad, because it's good because it means that we always end up having more exciting new things that, lead us in new directions. But it's bad because, of course, we don't foresee all of the potential ways it can go wrong either. But that being said, I can say where we stand today in terms of the different potential applications. And I'd say that the one that's most advanced, we haven't mentioned it much. It's not really quantum computing, but a way to use quantum particles such as entanglement, as we were discussing, to do communication, so to transfer information in a network, and also actually to replace our old, encryption based on factoring, which is currently the standard being used. But if that is vulnerable, we have to think about new kinds of encryption techniques that would not be vulnerable even if there was a quantum computer out there that hackers could use. So it turns out that quantum itself can be used to fight quantum hackers and quantum computers. So that's one thing that actually has been developed over the last couple of decades. And so there are ways to use quantum particles to develop unhackable encryption. And it turns out that from a technology perspective, it would be based on current technologies such as, lasers and, fiber optics that we've also been developing for many years. So that technology is fairly mature. It still needs to be improved in order to reach the tolerance levels of the noise and decoherence we would need. But it's getting there. And recently, for example, there's also been satellites launched that can do, quantum encryption or start sending entangled particles to different locations on Earth as a basis for starting to do quantum encryption. So it could become a satellite-based quantum encryption network. So those have, progressed very well in recent years. So I think that if I had to predict, I'd say that kind of quantum encryption-based communication networks are more likely to be, something we will be using more and more of in the near term. And then, as I was saying, for small-scale quantum computers, that could be merged with existing computers so that we have some kind of a hybrid system, and coupled with all of the machine learning techniques we're learning more and more, we could probably do some of this kind of materials design I was talking about. So small molecules for, developing, as I said, better energy sources, better chemicals, better drug development. Those could perhaps be improved in the small scale, in the nearer term over the next few years, decade. But then the large-scale hacking kinds of applications, such as breaking all of our passwords, luckily, I don't think, though, that will happen tomorrow. So I think we're safe, but we shouldn't be complacent because, as I said, even if it takes a decade or more, if we wait till then, it'll be too late. So we need to plan to move away from our current encryption right now.
Yeah.
So I guess that's the best I can do with prediction.
With predictions, yeah. And where was I thinking? So we're trying, and you're going back to entanglement again, because you're talking about how information then can pass from one point to another using entanglement, which is it's almost like teleportation, that you're almost teleporting information from one spot to another. Would that, can you do that then also for matter? I mean, for the particle in itself, or is it just the information that you can create that teleportation?
So that's right. It is an information teleportation. Indeed, this has been demonstrated, this protocol called quantum teleportation. And, it sort of reminds you of, these scenes from Star Trek or these science fiction shows, right, where somebody disappears in one location and reappears in another location instantly. Well, that's not, unfortunately, what we do in quantum teleportation, although it would be so convenient
cool.
right now,
right?
It
would be really cool.
But, yeah. However, it's still pretty cool because what happens is that if you have, let's say, some information that we have somehow encoded into an electron, then let's say a message, a quantum hello, let's say, then we can actually set up a protocol, where this one electron is entangled with another electron at a different location, and it could actually be a location at the other side of the universe, to be honest. And we can do a teleportation protocol where the information, that hello message in the one electron disappears, and it is exactly reconstructed on this other electron, which would have exactly the same message there. So it would, in essence, become the same as the first electron. So matter is not being teleported, and it's also not instantaneous. It takes, the time for light to travel for this kind of information to be transferred. So it's not instant, unfortunately, but it's at the speed of light. But it's effectively like recreating the matter because, of course, when you delete the information at one end, that electron is no longer carrying the message. So it's no longer has the identity of, what it was before. And that identity has now been transferred to the other electron. So in that sense, you don't need to transfer the matter, but you are, in a sense, transferring the identity. So it brings up, again, deep questions, right? At the human level, are we the sum total of all the information in us, or is there something more? So who knows?
Or is it our physical matter that gives us the identity or the information encoded in that matter?
Exactly. Isn't it amazing that now technology is forcing us to ask these very spiritual questions?
KIDO Talk Radio is 580 AM, KIDO Nampa, 107.5 FM Boise, Fox News Now.